Grade 5 pupils, we're looking at some further trig equations, part of the addition formula section of the course. This builds on trig equations that's found in Unit 1. In these examples, we have the option to substitute in our double angle formulas for sine 2x or cos 2x. The formula will depend on the information that is given. Okay, looking at example number 1. If we've got sine 2x is equal to minus sine x, this is unable to be solved in previous ways, so we have to consider a substitution. And in this particular case, what we're going to do is we're going to sub our equation for sine 2x. There's only one option for this, is 2 sine x cos x. Okay, so that substitution gives us 2 sine x cos x in place of the sine 2x. Bring everything over so it's equal to 0. Add sine x onto both sides is equal to 0. Okay, in this form, what we're looking to do is to factorise. Okay, if we're looking to factorise, it's not a typical trinomial, which we would maybe associate with factorising, but the very first thing we'd look at is our common factor. 2 sine x cos x plus sine x gives a common factor of sine x. 2 cos x plus a single sine x is equal to 0. In that situation there, by factorising, what we've created is essentially two trig equations to solve. So our first trig equation will be, how can that left hand side equal to 0? Well, it can equal to 0 if sine x is equal to 0, or it can equal to 0 if 2 cos x plus 1 is equal to 0. Okay, considering where our solutions must lie, sine x is equal to 0. From graph, x can equal to, we consider a sine graph, (0 to 360 for our sine, 1 and minus 1, that will occur 0, 180, 360. So x can equal to 0, 180 and 360. All solutions fall within the x values between 0 and 360 within the question. 2 cos x plus 1, very straightforward trig equation now. 2 cos x is minus 1, cos x is minus a half, x is our inverse cos of a half. Just separate this out, this solution, and inverse cos x of a half is equal to 60 degrees as part of our exact values. Cast diagram, not get lazy with our approach to our trig equation. And as always, we would look at this particular line. Firstly, we would consider our cos. So when is cos positive? It's positive in all, and C for cos, and therefore it's negative in the other two. And we have a negative a half, so we are considering our two negative values. So for this particular trig equation, x must equal to 180 minus the 60 degrees, and x must equal to 180 plus the 60 degrees. So 120 and 240. And again, both solutions fall between the 0 and the 360. So therefore, let's write out our final solution. X is equal to 0, 120, 180, 240 and 360. all solutions fall between 0 and 360 degrees. Okay, and that came from substituting in our double angle and factorising to solve our trig equation. Okay, in number 2, again, consideration of where our solutions must lie. This time we have our solutions, final solution must be in radians. And cos 2x is equal to cos x. We guide here, if we've got cos 2x and cos x within our question, which is what we have, then we keep consistency there, and we have the formula which involves the cos squared x. So we have consistency across the cos. Okay, so similar to the previous one where we subbed in sin 2x, and this one here, sub in cos 2x is equal to cos squared x minus 1. So cos 2x therefore becomes two cos squared x minus 1 is equal to cos x. Again, bring the cos x over, let's add it to both sides. Plus cos x, subtract cos x from both sides. Minus 1 is equal to 0. And again, we're going to have a very, very similar approach. And this time again, we're going to look to factorise. There's no common factor, so we're going to look to find a trinomial. Okay, to help, let's consider 2c squared minus c minus 1. How would you factorise that? Factorise it in the same way as you would factorise your cos. You would factorise your trig expression the same way as you would factorise a normal quadratic. So only way to get the c would be 2c and c. The only way to get the 1 would be 1 and 1, and therefore I have minus and plus to get me my minus c. Please factorise however you feel comfortable. So if I'm considering that as how to factorise a normal quadratic, if we've got a trig, essentially a trig quadratic, I can treat that as 2 cos x plus 1 cos x minus 1. Again, if you wish to multiply that out, you'll find that you would get back to the quadratic. Exact same situation as I had previous. I now have two separate trig equations to solve. I've got one that involves 2 cos x plus 1 equals 0, and I've got one which involves cos x minus 1 equals 0, and solve them separately. So cos x is equal to 1, and in this particular case, when is cos x equal to 1? 1 minus 1, so at 0 and 360 degrees is the 2 times that cos x is equal to 1. So x is equal to 0 and 360. In my left hand side equation, 2 cos x is equal to minus 1, cos x is equal to minus a half, Again, separating out, x is inverse cos of a half, which is 60 degrees. Very tight for space here. But my cast diagram, between 0, 180 and 360. Again, my key line is this line here. Is a cos, so positive for C, positive for A, negative for the other two. And I'm dealing with a negative term, so that is my two solutions there. So I have x is equal to 180 minus the 60, which is 120, and x is equal to 180 plus 60, which is 240. Okay, just ensure a wee separation between those two equations. Spacing is not great. So solution wise, x is equal to 0, 120 degrees, 240 degrees, and 360 degrees. 4 solutions. However, I need to go back to my question, and the solutions are looking for between 0 and 2 pi, so 0 and 360, but in radians. Okay, and you're converting in radians. We have 0, 2 pi over 3, 4 pi over 3, and 2 pi. Okay, that was very, very quickly changed. May need a wee bit of reminder in radians and a wee bit of work on the side if that's required. So 4 solutions within radians. Okay, next one. Again, we've got cos 2x within our trig equation. Again, what we're looking for is a solution in radians. Up to 2 pi, so up to 360 degrees. But this time we've got cos 2x and we've got sin x. So looking up to our formula to use. This time, because we've got the cos 2x, what we need to look at is the fact that we've got a sign in the question, and therefore we want to make our substitution sign. Okay, so first off we want to sub cos 2x is equal to 1 minus 2 sine squared x. Okay, so what we've got 1 minus 2 sine squared x is equal to sin x. Again, this time I'm going to take everything over. 2 sine squared x plus sin x minus 1. Again, like I said, the previous one, I'm going to consider this trig quadratic as a simplified quadratic. 2s squared plus s minus 1 is equal to the 0. So again, let's factorise that out. 2s and s, 1 and 1, and this time we have plus and minus. So if I can factorise that in a quadratic, that's going to simplify out to become 2 sin x minus 1 sin x plus 1. Again, same situation. Once I've factorised, what I've got is going to create two different trig equations. First bracket equal to 0. Second bracket equal to 0. Let's get a sine graph. It's going to help us solve. So when sin x equal to minus 1, so there's 1, there's minus 1, there's 360. So that value there occurs at 270. And my second equation, 2 sin x is equal to 1, sin x is equal to a half, so x is equal to inverse sine of a half, which is 30 degrees. Cast diagram dictates where my solutions lie, and again my key point is here, which gives me sine value is A is positive and S is positive, and the quadrants with T and C are negative, and I'm looking at a positive value, so I've got two solutions in here. So solutions are taken from x is equal to 30, x is equal to 180, subtract 30, which is 150 degrees. Therefore, x equals 30, 150, and 270. And once again, going back to where our solutions must lie, our solutions are between 0 and 360, but in particular in radians, so we have pi over 6, 5 pi over 6, and 3 pi over 2. Okay, so the start of each question, we have a substitution with our double angle, decision to be made which formula to substitute in, factorise to solve two different simple trig equations, and ensure the solutions match the question. So C, show my homework for specific questions to complete.